Hello, this video includes information on buffers.
So what we're going to deal with next are what are called polyprotic acids. Okay, it literally means more than one acidic proton. Okay, and when we look at polyprotic acids, a good example might be phosphoric acid, H3PO4. And the reason is if we were to look at phosphoric acid, it has 3 hydrogens in it, or 3 acidic protons. Well, when that acid reacts with water, only 1 acidic proton comes off of that acid at a time. So if we have phosphoric acid, the conjugate base of phosphoric acid is dihydrogen phosphate. So we're going to remove 1 hydrogen ion. It's going to join up with water. We're going to produce dihydrogen phosphate ions and hydronium ions. And the Ka value for this first step is 7.5 times 10 to the minus 3. But the conjugate base that's produced in the first step has hydrogen ions in it. It has acidic characteristics. So there's a second step in this acid ionization. So whereas the hydrogen or dihydrogen phosphate is the base in the first reaction, now it's going to act like an acid in the second reaction. It's going to lose another acidic proton to the water. Now we're going to produce hydrogen phosphate ions. Notice now the charge is -2 because we're losing a +1 charge. And more hydronium ions. But the Ka for the second step is much smaller than the Ka for the first step. And the reason for that is we're trying to remove a positive hydrogen ion from a negative ion. That hydrogen ion is going to be held more tightly in this acid than it was in the first acid. So this is a weaker acid than H3PO4. But again, if H2PO4, okay, dihydrogen phosphate is our acid, the conjugate base is hydrogen phosphate. And hydrogen phosphate also has a hydrogen ion in it. So we're actually looking at not just a polyprotic acid, this is specifically a triprotic acid because there are 3 acidic protons that can be removed. So if hydrogen phosphate is our acid, the conjugate base is phosphate. And notice that the Ka for that third step is even less than the Ka for the second step, because now we're trying to take a hydrogen ion away from something that has a -2 charge. And the phosphate that's produced in this third step doesn't have any acidic characteristics anymore. There's no hydrogen ions that can be removed. So we're done. It's a polyprotic acid, though, because there's more than 1 acidic proton that can be removed, and they get removed 1 at a time. And the strength, the first step is much stronger than the second step, and the third step is the weakest. And this first step is not very strong. Okay, this is a weak acid. This is a weaker acid. This is the weakest out of the 3. Now, there are several different polyprotic acids. We looked at phosphoric acid already. Okay, if we look at arsenic acid, it's a triprotic acid. It's got 3 acidic protons. There are 3 steps. And notice the Ka values get smaller and smaller as we go down. Carbonic acid is a diprotic acid. It has 2 steps. Sulfuric acid is diprotic, and it's actually unusual because the first acidic proton comes off 100%. Hydrogen or sulfuric acid to hydrogen sulfate is 100%. But when the hydrogen sulfate goes through that acid ionization, it only to a small percent carries out that second step. Sulfuric acid is diprotic, and hydrosulfuric acid is diprotic. Now, let's look at how these polyprotic acids are affected by their pH. So if we were to look again at phosphoric acid as our example, Okay, here's our acid ionization. The Ka equals 7.5 times 10 to the minus 3. Okay, we could say x squared over our concentration, and we could figure out what the hydronium ion concentration is. Okay, it's not here. We could do that, but we've worked on those kinds of problems already. So the hydronium ion concentration is 0.190. Now, if we were to look at the second step, the Ka for the second step is 6.2 times 10 to the minus 8. The hydronium ion concentration from the second step is significantly less than the first step. Okay, it's 10 to the minus 8.000000000062. And if we were to look at the third step, now the hydronium ions that we're getting from the third step is even smaller than the second step. Now, overall, we are producing hydronium ions here, and we're producing hydronium ions here, and we're producing hydronium ions here. So the total number of hydronium ions is really the sum of the three steps, but with significant digits, it's really just the first step. The amount of hydronium ions we get from the second step and the amount we get from the third step are almost insignificant relative to how much we had at the beginning. So to calculate the pH, we would just need that first hydronium ion concentration, and the pH is 7 or 0.712. Again, we're getting a little bit of hydronium here. We're getting a little bit of hydronium here, but it's insignificant. It's not going to change the overall hydronium ion concentration, and it's not going to change the pH of the solution. So polyprotic acids. What we're going to do now is we're going to talk about buffers. We'll define what they are first. We'll look at how we can calculate the pH for buffer solutions, and then we're going to add acids and bases to buffers and see what happens. So when we talk about a buffer solution is a solution that has the ability to resist changes in pH when limited amount of acids and bases are added to them. A buffer solution contains a weak conjugate acid-base pair. And therefore, there's something for the acid to react with, and there's something for the base to react with in the buffer solution to neutralize that acid or base that's added. So if we just look at this picture here, okay, we have a buffer solution here, okay, it has a pH of 8. And if we were to add hydrochloric acid to it, the pH really doesn't change. And there's an indicator in here that just shows us that the pH isn't changing. But if we have a buffer solution at a pH of 8, and we were to add a lot of acid, the buffer solution will eventually not be able to consume that acid anymore, and the pH is going to change. So let's calculate the pH of a buffer solution. So it says calculate the pH of an acetate buffer solution that contains 0.100 molar acetic acid and 0.12 molar sodium acetate. So the first thing we're going to do is we're going to write out our reaction. So we've got acetic acid, CH3COOH. Okay, you'd be given this. You don't need to memorize what that is. And we're reacting it with water. Okay, well, we know that acids donate their hydrogen ion. So the conjugate base of acetic acid is acetate ion. And the conjugate acid of water is hydronium. And we've got our arrow in two directions. Now, what's a little bit different about this kind of problem is that in our solution, we have acetic acid. Okay, we've got 0.100 molar acetic acid, but we also have acetate ions. So that means that our acetic acid is 0.100 minus X, because some of it's going to react. And the acetate ion comes from the sodium acetate. Okay, the sodium acetate completely dissociates. We have 0.12 acetate, and a little bit of it's going to react to establish equilibrium. And we're going to produce X amount of hydronium ion. Now, when we write our Ka expression, it's still products over reactants raised to the power of the coefficient in the balanced equation. So 0.20 or 0.120 minus X times X divided by 0.100 minus X. So we're figuring out that K expression the same way. Now, this is a weak acid. This is the conjugate base of a weak acid. So this is a weak base. That means this X and this X here are insignificant. Now, the Ka for acetic acid, you'd be given this, is 1.80 times 10 to the minus 5. This is a given. You look this up on a table. And now, because we're getting rid of this X here and this X here, 0.120 times X divided by 0.100. So we're going to multiply both sides by 0.100 and then divide both sides by 0.12, and that'll leave us with X. X equals 1.5 times 10 to the minus 5, and that's the hydronium ion concentration. We can calculate the pH. We take the negative log of the hydronium ion, and the pH of this buffered solution is 4.82. It's an acidic buffer. There's another way that we can calculate the pH of a buffer solution, and it's by using what's called the Henderson-Hasselback equation. So let's say we have this generic acid, HA, reacting with water. Okay, the acid's going to donate its proton to the water, so we're going to produce A- and hydronium ions. Okay, well, we know that the Ka expression are the products over the reactants. And we know that pH can be calculated by taking the negative log of the hydronium ion concentration. And if we were to take the Ka expression and kind of manipulate it a little bit to solve for the hydronium ion equals Ka times our acid over our base. All we're doing is solving for the hydronium ion by multiplying by the acid and dividing by the base. So what are we going to do with that from there? The pH can be calculated by taking the negative log of the hydronium ion concentration. And that equals the negative log of the hydronium ion concentration. And because the hydronium ion concentration equals Ka times our acid over our base, we can do a substitution. So we're going to take this and we're going to substitute it in for hydronium here. Now, if we have the negative log of Ka times the concentration of the acid over the base, we can distribute the log into our parentheses, and it gives us the negative log of Ka plus the negative log of our base over our acid. Now, that simplifies this a little bit. And the negative log of the hydronium ion, that equals pH. And the negative log of Ka equals this new value that we're going to call pKa. And we have the log of our base over our acid. So this here is what we call our Henderson-Hasselback equation. If we know the Ka and we take the negative log of the Ka, we can figure out pKa. If we know the concentration of the base over the acid, we can calculate the pH of the solution. So let's look at another problem. It says calculate the pH of an acetate ion if we've got 0.10 molar acetic acid and 0.20 sodium acetate. That's the same question that we had before. But this time we want to calculate the Henderson-Hasselback equation using the Henderson-Hasselback equation. So we have our reaction. It's the same as before. But now, rather than writing a nice chart and writing a K expression and solving for X and taking the negative log of that, we're going to use this equation here. So pH equals pKa plus the log of our base over our acid. So for pKa, we would take the negative log of Ka. The negative log of Ka gives us the pKa value. We're going to add to that the log of the base concentration over the acid concentration. Well, the sodium acetate breaks up into acetate ions, and the acetate ions are the base in our buffer solution. So the 0.12 goes on top. The acetic acid is the acid in the buffer solution, so 0.10 on the bottom. And when we plug that all in, we get 4.824. It's the same number that we got in the previous math problem when we were solving for the pH of the solution. It's a shortcut of how to calculate the pH of a buffer. Okay, so make sure that you have that written down someplace. It makes life much easier than having to do a Ka expression in solving for X for buffer solutions. So let's look at another one. Okay, this time we have 0.25 molar ammonia. Ammonia is a weak base. And we have 0.40 molar ammonium chloride. Well, that's a salt. It breaks up into ammonium ions and chloride ions. And the ammonium ions are going to be the acid part of our buffer solution. And we're given the Kb for ammonia. We want to calculate the pH of the buffer solution. Well, the first thing we want to do is write down that reaction so we know the chemistry that's involved. So we have the ammonia reacting with the water. Since ammonia is a base, the hydrogen ions going from the water to the ammonia, we're going to produce ammonium and hydroxide. So we're going to use our Henderson-Hasselback equation. pH equals pKa plus the log of our base over our acid. So I'm going to kind of go through the steps and see if you can do the calculation on your own. So we need the pKa. We're given Kb. So we're going to have to figure out Ka. And if we take the negative log of Ka, that'll give us our pKa. So we'll have this part of our Henderson-Hasselback equation. We're going to add to that the log of the base over the acid. Well, the ammonia is the base, and the ammonium ion is the acid in our buffer solution. So we're going to plug in 0.25 here. We're going to plug in 0.40 here. And we're going to use the Henderson-Hasselback equation to calculate the pH of the solution. So see if you can do it. Calculate what the pH of this buffer solution will be. All right, so for the Ka, I have 5.6 times 10 to the minus 10. I'm just taking the Kb value and dividing it into Kw. The negative log of Ka will give me pKa plus the log of the base, which is the ammonia, over the acid, which is the ammonium. And I get 9.05 for my pH for this buffer solution. We have a buffer solution, and let's say that this is our buffer solution here. Okay, we've got acetic acid reacting with water. We're producing hydronium ions and acetate ions. This is a buffer solution because it contains a weak conjugate acid-base pair. All right, well, we know by definition Buffers resist changes in pH when limited amounts of acid and base are added to them. Well, how does that happen? Well, if we were to add an acid to this buffer solution, it would react with the base in the buffer solution and drive the equilibrium in this direction. And in doing so, the acetic acid concentration will go up and the acetate ion concentration will go down. If we have this buffer solution and we add a base to it, the base is going to react with the acid component of the buffer solution, and the reaction is going to go in this direction. And we're going to increase the acetate ion concentration and decrease the acetic acid concentration. So if we have a buffer solution and we add an acid to it, it's going to react with the base in the buffer. And if we have a buffer solution and we add a base to it, it's going to react with the acid in the buffer. So the reason why buffer solutions work is because they contain both a weak acid and a weak base that can react and consume the acid or the base that we add to them. So let's look at a question. Okay, so we have a 0.390 molar hydrocyanic acid solution that also has 0.350 sodium acetate. So I have a weak acid and a salt of its conjugate base. So I have a buffer solution. It gives me the Ka for hydrocyanic acid is 4.9 times 10 to the minus 10. I want to first calculate what the pH of this buffer solution is. And then I'm going to take the buffer solution and I'm going to add some concentrated hydrochloric acid to it. How is that going to affect the pH of the solution? So let's not do the second part of this problem first. Let's just calculate the pH of this buffer. It's going to be the same as the problems we just did. So use the Henderson-Hasselback equation, okay? pH equals pKa plus the log of the base concentration over the acid concentration, and calculate the pH of the buffer solution. Okay, here's your Ka, calculate pKa. The cyanide in the solution is going to be the base, and the hydrocyanic acid in the buffer solution is going to be the acid. See if you can calculate the pH of the buffer solution. Don't worry about the second part yet. We'll do that part together. So here's our buffer solution. Okay, we've got our hydrocyanic acid reacting with water. We're producing cyanide and hydronium ion. Okay, this is our acid. This is our base. Okay, so pH equals pKa, which is the negative log of the Ka value, plus the log of the base over the acid. And I agree. Kind of just keep an eye on the significant digits. Again, you got three significant digits here, 3 decimals in your answer. All right, so now let's do the second part of this problem. We have this buffer solution. Okay, it's at equilibrium. The pH is 9.263. We're going to add an acid to this buffer solution. Well, acids react with bases. So the acid is going to react with the cyanide ions in our buffer solution. Acids react with bases. So the cyanide ion is going to react with the hydrochloric acid. Remember that hydrochloric acid is a strong acid. It breaks up into hydrogen ions and chloride ions 100%. Those hydrogen ions are going to be latching themselves onto water and they're making hydronium. So this comes from the hydrochloric acid that we're adding to our buffer. acids react with bases. So the basic component of our buffer solution is going to be reacting. We're going to be decreasing the acid or the cyanide ion, and we're going to be increasing the hydrocyanic acid. Now, these are going to react stoichiometrically, and they're going to react to completion. So we have 0.350 moles of cyanide ion. We're adding 0.020 moles of our acid. And we have 0.390 moles of our hydrocyanic acid. The base in the buffer solution is going to completely consume the acid that we're adding to it. So the acid is the limiting reactant. All of the acid reacts. We want that arrow in one direction. Now, it's going to react in a stoichiometric ratio. So if 0.0200 moles of acid is reacting, it's going to react with 0.0200 moles of the base in the buffer. And it's going to produce 0.0200 moles of our acid. So once all of the acid has been consumed, the ratio of base to acid in the buffer solution has changed just a little bit. It's in a 1 liter solution, so the number of moles equals the molarity. So now we can calculate what the new pH is going to be after we add this acid to our buffer solution. So the negative log of the Ka gives us pKa. But now the values of our base and our acid have changed slightly because the buffer consumed the acid we added to it. So now the base is 0.330 and the acid is 0.410. So the pH does go down just a little bit, but it doesn't go down nearly as much as if we were to add that acid just to water. And that's what buffers do. Okay, now, it's a 1 liter container. It tells us that 1 liter solution. The volume here will cancel out with the volume here. We don't really have to put it in there, and in the future, we don't have to show it. Even if it's not a 1 liter solution, this volume number here will cancel out with this volume number here. So again, the pH decreased when we added the acid, but it only decreased by 0.047. It was 9.263. Now it's 9.216. So buffer solutions resist large changes in pH by either consuming the acid or the base that's added to them. So let's take that same buffer solution, and this time we're going to add sodium hydroxide to it. Well, sodium hydroxide is a base. It's a strong base. And the hydroxide ions from the sodium hydroxide are going to be consumed by the acid component in the buffer solution. Again, acids react with bases, bases react with acids. So let's look at what we have. We're adding sodium hydroxide to our buffer solution. The sodium hydroxide breaks up into sodium ions and hydroxide ions. The sodium ions are spectator ions. The base is going to react with the acid in the buffer solution. And strong acids and strong bases react to completion. So we're going to make another ice chart. Okay, our buffer solution was 0.390 moles in 1 liter. And the cyanide was 0.350 moles per 1 liter. And now we're adding a strong base to it. And again, that strong base, as long as we're within the limits of the buffer, is going to be completely consumed by the acid component in the buffer. So none of that sodium hydroxide will be, none of the hydroxide will be remaining. We've decreased the acid concentration in the buffer a little bit, and we've increased the base in the buffer solution by a little bit. So now we know Ka, we actually calculated pKa, so we really know pKa. We know the base, we know the acid, we can calculate the new pH. So the pKa plus the new concentration of the base over the acid. And this one actually is a little bit different because the concentration of the base and the acid in the buffer solution are equal to each other. 0.370 divided by 0.370 equals 1. And the log of 1 equals 0. So the pH equals the pKa. And we added a strong base to the buffer solution, but the pH, again, only went up marginally. It only went up by 0.047. And that's the function of a buffer solution. It will consume strong base or strong acid that's added to it. And it only changes the pH a little bit. So let's look at kind of a comparison. Let's take some sodium hydroxide and add it to an unbuffered solution. Okay, that means that we don't have an acid in the solution to react with the sodium hydroxide. And it tells us that the unbuffered solution has a pH of 9.267. Well, the hydroxide ion concentration is going to be 0.0200. Okay, it comes from the sodium hydroxide. It's a 1-to-1 ratio. We want to calculate the hydroxide ion from the unbuffered solution. Well, we know the pH. And if we know the pH, we can calculate the pOH. And if we know the pOH, we can calculate the hydroxide ion that's in the unbuffered solution. So if we were to take the pH and subtract it from 14, that gives us the pOH. If we take 10 to the negative pOH, that'll give us the hydroxide ion concentration. Now, we have hydroxide from the sodium hydroxide, and we have hydroxide from the unbuffered solution we're adding it to. So the total hydroxide ion concentration is going to be the sum of the two. But 1.8 times 10 to the minus 5 is insignificant relative to 0.0200. So the hydroxide is coming from the sodium hydroxide, not from the unbuffered solution. So the pH is going to go from 9.263 up to 12.301. So the pH has a huge jump, a huge increase, because we're adding a strong base to an unbuffered solution. So buffered solutions resist changes in pH. Unbuffered solutions don't have components in them to consume the acid or the base we're adding to them, so there's going to be big changes in pH. When we talk about buffers, buffers have a capacity. They can't take an infinite amount of acid or base and consume it. So buffers have the ability to prevent changes in pH within reason, as long as small amounts of acid or base is added to them. So the buffer capacity is the amount of acid or base that can be added without significantly changing the pH of the solution. So here we have a solution, okay, and it's got a pH of 8, and it's a buffer solution. And we add a little bit of acid to it, and the pH goes down a little bit. But the buffer resisted the change in pH because we were within the limits of the buffer. We were within the buffer capacity. But if we continue to add acid, eventually we will exceed the capacity of the buffer. And then any additional acid we add is going to really lower the pH of that solution. So buffers can't resist changes in pH forever, just within small quantities. And it depends on how much conjugate acid base are in the buffer solution to begin with. Okay, how do we prepare a buffer solution? Okay, well, we can use the Henderson-Hasselback equation to figure out how much base and acid we need to add in order to get to a particular pH. And if the base concentration is equal to the acid concentration, this ratio becomes 1. The log of 1 equals 0. So pH equals pKa. So when we look at a buffer solution, we want to have the concentrations of the acid and base in that buffer solution to be equal to each other, or at least to be close to each other. So when we go to choose which buffer solution we want to use, we want the pH to be as equal or as close to the pKa as possible. And we want the acid to base ratio in that buffer solution to be somewhere between 10 to 1. So let's say that we're given 3 possibilities for a buffer solution we want to make. We could make a buffer solution out of acetic acid and acetate ions. We could make a buffer solution between carbonic acid and hydrogen carbonate ions. Or we could make a buffer solution between hypochlorous acid and hypochlorite. And let's say we want to make a buffer solution that has a pH of 7.200. Well, which buffer solution is going to be the most effective? Well, what we want is the pair that's going to give us the pH or the pKa as close to the pH as possible. So we look up the Ka for acetic acid and the Ka for carbonic acid and the Ka for hypochlorous acid. And then we take the negative log of these numbers and we get our pKa values. So the pKa for acetic acid is 4.745. The pKa for carbonic acid is 6.367. And the pKa for hypochlorous acid is 7.456. Which one would be the best for making a buffer solution at a pH of 7.200? Well, this one's the closest to 7.200. So we would want to use hypochlorous acid and hypochlorite. We want to make a solution with a pH of 7.200. So I'll plug that in for our pH. The pKa is 7.456. And then plus the log of our base over our acid. All right, so how are we going to prepare our solution? Let's subtract 7.456 from both sides. That gives us negative 0.256 equals the log of our base over our acid. All right, well, we want to get rid of the log. So we'll just take 10 to the x on both sides. That cancels out our log. And we get 10 to the negative 2.56 equals the concentration of our base over our concentration of our acid. So if we plug this into the calculator, we get 0.555. Okay, well, what does that mean? It means the ratio of the concentration of the base to the concentration of the acid is 0.555 to 1. So if we wanted to make a buffer solution that has a pH of 7.200, we would need 1 molar hypochlorous acid combined with 0.555 molar hypochlorite ion. This would come from sodium hypochlorite, but the sodium is a spectator, so it doesn't matter. And if we mix these two solutions together, the pH of that buffer solution will be 7.200. Now, let's say that we wanted not the concentrations, but we wanted the masses. We're going to do the same kind of thing. Okay, this time we're going to use an acetate acetic acid combination because the pKa will be the closest to the pH we're looking for. Okay, and we can kind of ballpark this in our heads. If this was 1, the pKa would be 5. So this is going to be a little bit less than 5. All right, we're going to do the same kind of thing. We're going to use our Henderson-Hasselback equation. We're given the pH that we're looking for. We're given the Ka so we can calculate the pKa. Okay, so pH equals pKa plus the log of our base over our acid. pKa is calculated by taking the negative log of the Ka value equals the concentration of our base, which is the acetate ion, over our acid, which is acetic acid. Well, we know what pH we want. We want a 5.00 pH buffer solution. All right, what are we going to do now? We're going to subtract 4.75 from both sides. So 0.25 equals the log of our base over our acid. Okay, well, we want to get rid of the log function. So we're going to take 10 to the x on both sides. That gets rid of the log on the right-hand side of the equation and gives us 10 to the 0.25 on the right-hand side. We can plug this into the calculator and we get 1.78. That's the ratio of base to acid that would give us a pH of 5.00. But this time the question doesn't want to know what's the concentration. It wants to know what are the masses. Well, we know the concentration ratio. And we know we have a 1 liter solution, so we know the moles. And if we know the moles and we know the formulas, we can figure out the grams. So the mole ratio is going to be 1.78 base to 1 acid. The acetate ions, where do they come from? Well, we can't just get a bottle of acetate ions from a stockroom, but it can come from sodium acetate or any kind of salt that has acetate in it. Sodium is usually the kind of go-to cation that we use. So if we know the moles of the base, we can figure out the grams. So 1.78 moles of sodium acetate can be converted to grams by looking up the molar mass of CH3COONA. That's where that 82.03 comes from. Now we're going to do the same thing for the acetic acid. We have 1 mole. Here's our mole ratio because we're in a 1 liter solution. And we're just converting moles to grams. 60.06 is the molar mass of acetic acid. So what does that mean? How would we make this solution? Well, if we took a 1 liter solution that contains 60.06 grams of acetic acid and 146 grams of sodium acetate, mixed together, the pH of that buffer solution is 5.00. And then once we know the pH of the buffer solution, we can figure out if we were to add an acid or add a base, how would the pH of that buffer solution change? Would we be within the buffer capacity where there'd only be marginal changes? Or would we exceed the buffer capacity and then there would be big changes?